So let's continue to look at some other node voltage examples. So in this particular example, you'll notice we're already given our reference node and our node voltages are already labeled. So essentially our steps 1 and 2 have already been done for us. So steps 1 and 2 were done for us in this problem. And so I'll mention this problem comes from page 88 of the textbook if you want to look at that a little closer. And what we're trying to find here is we want to find this current which is in green. So we want to find I through our 2 ohm resistor. Okay, so steps 1 and 2 were already done for us, so let's then start in on step 3, right? So we're starting in on step 3, which is writing those KCL equations at each of our essential nodes that is not the reference node. So we can go ahead and note, before we even get into step 3, we know we have 3 essential nodes, right? Because we have 1 here, we have 2 here, and then this whole bottom part is our reference node. So we have n sub e equals 3. And so we know we're going to need n sub e minus 1, 3 minus 1, which is of course 2 equations. So we know we're looking for 2 equations. So ideally, an equation from node 1 and an equation from node 2. So let's do our KCL equation at node 1. So we can define our currents as leaving by convention, right? So we have currents coming this way and so on, one going in each direction. So for our current going out the left, we can use that little equation that I had written before, or we can go through explicitly and use Ohm's law and KVL, whatever works better for you. As you're getting comfortable with it, you don't even necessarily need to write or reference this equation. You just kind of get comfortable doing it in your head. But if you're not there yet, don't feel bad. It does take a lot of practice before you can get comfortable, and everybody gets there at a different pace. So if we're talking about our current going out the left of node 1, we have V1 minus 14 divided by 4. Current going out the bottom from Ohm's law is going to be V1 divided by 3. And now our current going out the right, notice we have that same issue that we ran into, or almost ran into, with our bridge circuit in a previous video, where we don't have a resistor here, we just have a voltage source. So we don't really know what this current is going to be. We know ultimately that's equal to 0, but the reason is because this current in our ideal source doesn't follow Ohm's law. And this is an ideal voltage source. The same way we talked about, it's an idealization, like you might talk about a frictionless surface in physics. So current in ideal voltage source does not obey Ohm's law. So that means we can't draw some relation between the current going through this to find some resistance and then relate it to our node voltages with KVL. So we have this issue. We don't know what this current is here. So how do we get around this? And so the answer is we can define what's called a supernode. So our solution is to define a supernode that combines nodes 1 and 2. And so I'll draw it out a little bit in a second, and hopefully that'll help it make a little more sense. That combines nodes 1 and 2, which are on either side of the voltage source. One important thing to note is that our original node voltage definitions are unchanged. So our V1, V2, and our reference node do not change at all. So unchanged, so very important point. But of course, the whole solution thing here is to define a supernode. So let's go ahead and put our circuit back in here. Let's move it over here. That looks good. Okay, so what we're doing when I say we're defining a supernode is really we can kind of come in here and just think of this whole thing as being a big amorphous node. So we've combined node 2 and node 1 into one node. And so that combined node is what we call our supernode. But we still have our definitions V1, V2, our reference node is still in the same place. So nothing has changed in terms of that. So now, if we do what we tried to do before and define our currents as leaving, we can say, looking at this whole big blob of a node, we have a current I1 going out the left, a current I2 going out the bottom left, a current I3 coming out the bottom right, and a current I4 coming out the right. It's also worth noting we could, of course, combine our 6 and 2 ohm resistors because they're in parallel. However, we note that ultimately we're trying to find this current I through our 2 ohm resistor. So if we do combine those resistors to find our node voltages, at the very end we'd have to split them back apart in order to find that current I. Okay, so we've got the supernode. So now instead of writing a node 1 and node 2 equation, what we can do is we can write a supernode equation. So we can say the equation for our supernode is going to be equal to, we just do the KCL, right? So we have I1 plus I2 plus I3 plus I4. So all of those are going out and zero current coming in. So we've just done our KCL here. So of course we can do Ohm's law and KVL. I'm kind of going to combine both of those steps together to say that our I1 is going to be V1 minus 14 divided by 4. Same as we saw when we were initially trying to write our node 1 equation. We have V1 over 3 is equal to I2. We have V2 over 2 is equal to I3. And then finally we have V2 over 6 is equal to I4. All of that equal to 0. If we want to get rid of that fraction and clean that up a little bit, we can multiply by 12. And if we multiply by 12 and collect terms, what we end up with is 7V1 plus 8V2 equals 42. So this would be our supernode equation. So notice we have now one equation, but we have two unknowns. So we have V1 and V2, which are both unknown. So we can't solve for V1 and V2 because we just don't have enough information. And so what we're going to see is we still need our two equations. So remember way back at the start we said n sub e minus 1, in this case was 3 minus 1, was two equations. So we still need this. So we still need 2 in this case. That doesn't change, but what changes is where we get those two equations. And so we're going to get our second equation from looking inside our supernode. And so I'm going to put that in quotes, looking quote unquote inside the supernode. We can also call this our supernode constraint equation. And essentially all that is we're going to be looking inside here and we're going to say how do V1 and V2 relate to one another through the supernode. So let's look at that. Let's copy the circuit or paste the circuit one more time here. Okay, and let's draw our supernode here. Right, so this is still our supernode. And so what we're going to do then is we want a supernode equation, a supernode constraint, sorry. We already have our supernode equation, that's what we did previously. Now we're looking for this supernode constraint. And so the way we're going to get that is we're going to do a KVL around this loop here. And again, as is always the case with applying our Kirchhoff voltage law, we can start in any point along the path and go in either direction. We just have to make sure we end and start at the same place. The way I've written it here, we could maybe start down here and go clockwise. And if we do that, what we'll get is negative V1 minus 6 plus V2 is equal to 0, which we could, of course, rearrange if we want to be V1 minus V2 equals negative 6. And so here is our second equation that we then can combine with this other circled equation to solve for our two unknowns. So let's go ahead and do that using our matrix method. Again, this would be simple enough to do with substitution or linear combination, but just getting the hang of our matrix method, preparing ourselves for those more complicated circuits. So our coefficient matrix, our first row comes from this top equation. We see we have 7 and 8 as our coefficients. So we have 7 and 8. We know this matrix is going to be inverted. Our second row of coefficients comes from our second equation, which is 1 and -1. Our constant matrix we have from our first equation, 42. And from our second equation, -6. We have 42 minus 6. So if we plug that in our calculator, we get that V1 is minus 0.4. V2 is 5.6 units of volts, since we had everything in ohms and amps. Okay, but we were initially asked for the current through this 2 ohm resistor, so we had some current defined like this. And so we can pretty easily see from Ohm's law that that current I is just going to be equal to V2 divided by 2. And we plug in our 5.6 and we see that that is 2.8 amps. Okay, so this example showed us how we can use Supernode if we ever run into a case like this, where we have only a voltage source that's between two essential nodes where neither of those two nodes are the reference node. If anybody has any questions about when to use a Supernode or how to use a Supernode, please don't hesitate to let me know.